Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this ninth lecture of mineralogy series, and in today's lecture we will try to understand how to calculate the mineral formula of different silicates. And in the last lecture we basically learned about the phase relation of binary system. We started with a eutectic system in which we took two different solid which are not miscible, but your liquid was miscible, and then we try to take a example of fractional crystallization and equilibrium crystallization, and try to see when your melt is crystallized, in case of equilibrium crystallization how it behaves, and in case of fractional crystallization how it behaves, and what kind of rock will form in a your binary eutectic system. We also try to understand that when you try to melt a rock in a equilibrium condition, how your binary eutectic system will behave. And then we took a second example of your binary solid solution system, and we try to understand this equilibrium crystallization of the melt and fractional crystallization of the melt, and as well as your rock will melt at high temperature. So, in today's lecture we will basically try to calculate the mineral formula of some rock forming minerals which is abundant in crust and in the mantle, and these to perform this kind of calculation you basically need their oxide concentration, and these oxide concentration are basically measured using a instrument, some sophisticated instrument called electron probe microanalyzer. And so basically this electron probe microanalyzer, these are the instrument which is widely used in earth sciences to calculate to measure the composition of the minerals. So we have this instrument which is called as electron probe microanalyzer, and abbreviation is EPMA, and this instrument is widely used in earth sciences to precisely measure the chemical composition of the mineral, even if your mineral is very small, which you cannot identify using a petrological microscope. You can go to this instrument and you can analyze your mineral, and this instrument is used after 1960s, but previously people were using a wet analysis. So the second type of analysis which was very popular in analysis, and this wet analysis was very popular before 1960s. So what scientists were doing or geologists were doing, they were crushing the mineral and make a very fine powder of the mineral, and it is a destructive method. And the electron probe, because it's a just you use a beam of electron, very fine beam of focused electron that is interact with your sample. So this is a non-destructive method, and this wet analysis is a destructive method. So before 60s people are using this analysis. So what basically they were doing, they were crushing the rock or the mineral, and then they try to make a fine powder of these minerals, and they put it in a solution, and depending on the different density, the oxide which are present in these different minerals will sink or float, and then they will try to take out these different oxide which are present in your mineral and dry out, and they will weigh these different oxide which are present, and from that they are trying to measure the weight percent of different oxides are present in the particular mineral. Okay. So in before 1960s most of the analysis were reported in the form of weight percent of oxides. So when electron probe was used in earth sciences to measure the chemical composition of the mineral, so they also the company also started to follow the similar pattern, and most of the analysis given by this instrument is in the form of different oxides. Okay. So, you can basically compare the data before 1960s and after 1960s using a electron probe or previously by the wet analysis. And the only problem in the electron probe is that it cannot distinguish the different valency state of iron or any other element. So, it gives a more, basically we assume that all the iron present in your mineral in the form of Fe2 plus. Okay. In case of wet analysis, you basically get Fe2 plus concentration and Fe3 plus concentration, but here if we consider that all the iron is present in our mineral is Fe2 plus, and later we can calculate based on the stoichiometry and the charge balance, we can calculate the Fe3 plus concentration. So, we will try to learn this in today's lecture. So, in the electron probe, we get a oxide percentage, and also these instrument, this electron probe microanalyzer, it cannot measure the concentration of oxygen precisely. So, that is why most of the analysis present in the oxide percent. They combine, they believe that these cations are combining with oxygen, and then it gives a concentration of that particular oxide. So, basically if you see the analysis of any mineral present, analysis of any mineral in which you want to know the concentration of different cations. So, your electron will give basically your concentration of oxide, for example, SiO2, then you have a TiO2, then you have a Al2O3, you have chromium oxide, you have FeO, you have MgO, you have MnO. So, all the major oxide concentration you can precisely measure using the EPMA. Then you have a calcium oxide, then you have a Na2O, you have a K2O, and if P2O5, nickel oxide, all these elements are present. So, you can measure the concentration of the oxide in the form of oxide in the particular mineral. So, these minerals, in the mineral, these oxide concentration would be present, and you can precisely measure the oxide concentration using a EPMA, and you get this concentration in mass percent, that is in a weight percent. Okay. And we basically write down the oxide, this different oxide in the form of higher charge and with smaller size. So, if you see here, silicon is 4 plus, titanium is also 4 plus, then you have a aluminum, that is a 3 plus, chromium 3 plus, then you have a iron. We already discussed that iron is present in the 2 plus state. So, here it is a 2 plus, Mg 2 plus, Mn 2 plus, calcium 2 plus, then sodium 1 plus, potassium 1 plus. So, basically when you come from top to bottom, the charge of cation is decreasing and the size is increasing. Okay. So, in this form most of the papers and in the textbook you will find the analysis of different oxides, okay, or different silicates. So, basically if you know the concentration of different oxides present in the particular mineral, from that you can calculate the mineral formula of that particular mineral. Okay. And in today's lecture we will try to understand how to calculate, or today we will try to learn how to calculate the mineral formula for different silicates. Okay. So, basically we will use a program which is your Excel program. Okay. And in this Excel program we have this program is very helpful and to calculate the mineral formula, and I believe that you have some idea about this program, Excel program. So, we will start with a Alvin, and we know that the formula of Alvin is your general formula is x2 y O4, where x is your 6-fold coordination and y is in your 4-fold coordination. Generally, Si and aluminum will go to the 4-fold side and magnesium and iron will go to the 6-fold side. So, the total number of cation present in the Alvin is always 3. So, total number of cation in Alvin is always 3. So, we will try to calculate the mineral formula of Alvin based on a 3 cation, and we will believe that all the iron present in the Alvin in the form of Fe2 plus. Okay. To do that, what we should do, first we should try to write down the oxide which are present in your analysis. So, we already have the analysis of your electron probe. So, this is these are the concentration of different oxide present in your Alvin analysis. So, these are the major elements or major oxides are present in your Alvin and from the electron probe. So, what we will do first, we will try to write down the different oxide present in this analysis, and in the next step what we will do, we will try to calculate the molecular weight of these different oxide, and it is a very simple. You know the atomic weight of silicon, you know the atomic weight of oxygen, because in SiO2 you have a 1 atom of silicon. So, 1 multiplied by the atomic weight of silicon plus you have a 2 oxygen atom in this analysis. So, 2 multiplied by the atomic weight of oxygen. So, if you do that, you can easily calculate the molecular weight of SiO2. Similarly, we will calculate the molecular weight for TiO2, Al2O3, FeO, MnO, nickel oxide. Nickel is very abundant in Alvin, sometime up to 5000 ppm of nickel could be present, and it is widely used as a geothermometer also. So, nickel is very important in Alvin analysis. So, whenever you analyze the Alvin, you should include nickel in the analysis, chemical analysis. And then you have a MgO, that is a 40.31. So, you can basically calculate the molecular weight using a periodic table if you know the atomic weight of different these cations, and you know the atomic weight of oxygen. So, you can easily calculate the molecular weight of different oxide present in your mineral. Okay. The next step is we should write down the total number of cation present in this oxide. Okay. What does it mean? That in SiO2 you have a 1 silicon atom, 1 cation of 1 atom of silicon is present. So, we write down 1 here. Similarly, in titanium oxide you have a 1 titanium atom, you have a 2 aluminum atom in Al2O3, you have 1 iron atom in FeO, you have 1 Mn in MnO, you have 1 nickel atom in NiO, and you have 1 atom of MgO, 1 magnesium in MgO, and similarly 1 calcium atom in calcium oxide. So, in the second step we will write down the total number of cation present in this different oxide. In the third step what we will do, we will try to write down the net charge of the cation present in these different oxides. Okay. So, we know that silicon is +4 charge, titanium is also +4 charge, aluminum is +3 charge, your FeO is your +2 charge, Mn is +2 charge, nickel is +2 charge, magnesium is +2 charge, and calcium is +2 charge. Okay. So, we will write down the different the charge of different cations in this cell, and then we already know the chemical composition of Alvin, and this composition is from the very famous Alvin from one mantle xenolith, that is a KLB1. So, KLB1 is in the New Mexico in America. There is a location which is known as a Kilborn hole, and in this Kilborn hole lots of these mantle xenoliths are coming out, and there in this peridotite, this KLB1 is a peridotite, and we know that in peridotite you have abundant of olivine. So, more than 40% of olivine, if the ultramafic rock has more than 40% of olivine, then it is called as a peridotite. So, KLB has abundant of peridotite olivine in this peridotite, and this peridotite is close to a fertile peridotite, that is a pyrolytic in composition. So, these samples are very important, and to know about the metal composition. So, in this KLB1 you have olivine, and this is the analysis of the chemical composition of the olivine, and this analysis is measured from the electron probe. So, EPMA. So, already we have a oxide concentration in this olivine, and we do not know that what would be the formula of this olivine and what would be the end member forsterite and fayalite proportion in this olivine, and we will try to calculate this. Okay. So, our first step is to we should try to see that what is the total of this analysis. Okay. That is a very important step, because if our analysis is not perfect, if our analysis is not correct, in that case our calculation will be wrong. So, we should try to use this function, that is equal sign sum, and in the bracket you should add all the oxide present in this analysis, and when you enter you get a total percentage of olivine. Okay. So, olivine give a total close to 100.13, and this 100.13 total is very close to 100%. So, when you analyze your mineral in EPMA, and if a mineral is anhydrous, means there is no hydroxyl group is present. Okay. So, your total should be close to 98.5 to 100.5 weight percent. If your total is between 98.5 to 100.5 weight percent, your analysis is good if the mineral is anhydrous. Okay. And if the mineral is hydrous, for example, amphibole, mica, all these minerals are if present. So, always these minerals contain some amount of water, and your total will be always less than 100%, because you have some structural water present in amphibole and in mica. So, in that case your calculation, your measurement is not wrong, it is correct. But if you have an anhydrous mineral and the total is less than 98.5 or more than 100.5, so this is basically due to the some error in your instrument. Okay. You should try to check the calibration and other step in the EPMA, or your sample has some inclusion. So, maybe you analyze your mineral with some inclusion, or maybe your some other issues in your analysis. For example, if your surface is not flat, or you use a very thick carbon coating. So, all this could be a possibility for your error in the analysis. But if your result is between 98.5 to 100.5 for the anhydrous mineral, so in that case your analysis is pretty good. Okay. So, in this particular analysis, if you see, your total is close to 100.13. So, it is in the range of 98 to 100.5 weight percent. So, this analysis is pretty good, and we can use this analysis for the calculation of your this mineral formula. Okay. So, in the olivine we know that we have this makes a solid solution between forsterite and fayalite. So, basically it has major oxides would be your SiO2, your FeO, and your this MgO. So, these three oxides are almost like 99% are present. Okay. So, now we have to calculate the mineral formula for this olivine. So, what we will do? We will first try to calculate the atomic proportion of different oxide present in this analysis. Okay. So, to calculate the atomic proportion of different cations present in this analysis, what we should do, we should basically take weight percent of that particular oxide divided by the molecular weight of that oxide, multiply by the number of cation present in that particular oxide. What does it mean? So, suppose you want to calculate the atomic proportion of silicon. Okay. To calculate the atomic proportion of silicon, what we should do, you should use a equal sign in this Excel program, and then we should take a cell that is your B14 cell, okay, that is the weight percent of SiO2, divided by a B4. B4 is your molecular weight of your SiO2, and then multiply by your total number of cation present in your SiO2. Okay. So, that is 1. So, I am using a dollar sign in front of the letter C and in front of the letter B. The main reason is that in the next row, when we want to calculate the titanium, aluminum, magnesium, iron, so we should not do again and again, just if we scroll the cell. So, if we move the cell, so automatically it will give a titanium, aluminum, iron and etc. these different cation proportion. Okay. So, this sign is very useful. So, once we do this, and when we already put these cells and press enter, it gives a proportion of your basically a silicon atom in this analysis. So, in this analysis we have a 0.669 atomic proportion this silicon present in this olivine, and if we use scroll down, so we can, this program, Excel program, will automatically calculate the proportion, atomic proportion of different cations present in this mineral. Okay. And so, you see that you have this proportion of different cations in this analysis, and when we try to add, these, the total number of atoms present in this olivine, it is always so in this analysis it is close to 2.016. Okay. And because we want to calculate this mineral formula based on 3 cations, so we have to normalize this concentration of this atomic proportion of different cations based on 3 cations. Now, our total is 2 cation, so we will normalize these to a 3 cation, and when we normalize it, so what we will do, we will take a proportion of silicon, that is your 0.669, multiply by 3 divided by the total number of cation in this analysis. Okay. So, we have to normalize to 3, so multiply by 3, and our total for this analysis, atomic formula per unit, is your 2.016. So, we will divide by this cell, that is a B35 cell. What I am doing here, I am using a dollar sign for in front of the letter and in front of the number. So, when you use a dollar sign in front of B and in front of 35, so basically in the next analysis, when you calculate the titanium proportion, it will be always, it will take a B35 cell. If you will use a dollar sign in front of the B, so it will move to the B36 when you take a titanium proportion normalized to 3 cation. So, because we already fixed the total proportion, and when we scroll this one to here, okay, so we get a proportion of different cations based on 3 normalized to 3 cation. Okay. So, these are the concentration of silicon normalized to 3 cation. So, we can add the total number of cation from here, and it is close to 3, and so these are the your final proportion of different cations present in this olivine analysis. And when you try to do this, okay, so you should at the same time you should also see the stoichiometry, because in the formula of, if you remember the formula of your if you use a if you remember the formula of your olivine, so olivine has a MgFe2 SiO4. So, if you see the total of magnesium and iron atom, that is total 2 atom of magnesium and iron is present in your olivine analysis, and silica atom is 1. So, basically the total proportion, if you see the magnesium plus iron in this analysis, okay. So, if you add the total proportion of magnesium atom and the total proportion of iron atom in this analysis, that is close to your 2, okay, and silicon is very close to 1, okay. So, it gives you a 2:1 ratio, okay. So, it means that your calculation is good, your calculation is correct, and it gives exact the same stoichiometry what we have in the general formula. So, up to this step you can find the proportion of different cations in this olivine mineral, okay. Now, the next step is to calculate the end member. So, we know that in olivine we basically have a phosphorite and phyllite, and phosphorite is basically a Mg end member and phyllite is a iron end member. To calculate the Mg end member in olivine, what we should do? We should take a Mg number of this your this analysis. So, Mg number is basically your Mg number is basically molar Mg divided by Mg plus Fe multiply by 100. Molar Mg divided by Mg plus Fe means that you can also write down this weight percent of your MgO divided by molecular weight of MgO divided by weight percent of MgO in your olivine analysis divided by molecular weight of MgO plus weight percent of FeO divided by molecular weight of FeO, and if you multiply this with 100, that will give you your this Mg number. So, basically it is a molar Mg divided by Mg plus Fe ratio, okay. So, to get this, what we will do to calculate the phosphorite proportion, what we will do? We will take we already have a molar this atomic proportion of Mg. So, to calculate this, we will take a atomic proportion of Mg divided by atomic proportion of Mg plus Fe multiply by 100. So, that is will give you the phosphorite proportion, and to calculate the phyllite proportion, we should take a Fe proportion divided by Mg plus Fe proportion multiply by, so atomic Fe in this olivine in olivine analysis divided by Mg plus Fe multiply by 100. So, this is basically your Fe number. So, if you do this, so from this you can calculate the end member of the olivine in this analysis, and you see that in this analysis you have almost 87% of phosphorite, and you have a 12% of your phyllite, and in the mantle olivine you basically a phosphorite content is close to your if you see most of the analysis in the mantle olivine. So, phosphorite will vary from 88 to 92 this phosphorite content. So, most of the mantle olivine have phosphorite content vary from 88 to 92. So, this is a typical ultramafic olivine composition, and using this Excel program you can easily calculate the end member and mineral formula of this olivine. Okay. But in this calculation we consider that most of the iron present, all the iron present in this olivine analysis is basically a Fe2 plus. But we also know that there are some silicate mineral in that you have a Fe3 plus, for example garnet. Okay. Garnet can contain a some proportion of Fe3 plus, okay, because it has a Fe3 proportion, some end members are present. So, to calculate that to mineral formula in which you have a Fe3 plus proportion, because in the electron probe we consider that all the iron is present in the form of Fe2 plus. So, we have to calculate the Fe3 proportion in your garnet analysis or other mineral in which Fe3 plus is present, and that is based on the stoichiometry and from the charge balance. So, in the next calculation, in the next example, we will try to calculate the mineral formula for garnet, and we will try to calculate that how much Fe3 plus is present in the garnet, and we will also try to see that what are the end members present in the proportion of end member present in this particular analysis. Okay. So, like in olivine we only focus on the total number of cation. So, in the general formula for your garnet you have general formula is your X3 Y2 Si3 O12. So, if you see the total number of cation which is present in your garnet is your 8. So, 3 plus 2 plus 3. So, in this calculation we will calculate based on 8 cations, okay, and these are basically a 2 plus cation, these are 3 plus cation, and these are 4 plus cation. So, if you see 3 multiplied by 2, so that is a 6, 2 multiplied by 3, 6, 6, 6, 12, and then 3 multiplied by 4, that is your 12. So, your total charge is 24 in the garnet analysis. Okay. So, to calculate the mineral formula, what we will do, we will write down we will follow the similar procedure, and we will write down the different oxides that is present in your garnet analysis. Okay. And now in this analysis we will include the Fe2O3, that is your hematite. So, hematite has only Fe3 plus. So, we will write down the molecular weight of Fe2O3, and in Fe2O3 we have a 2 Fe3 plus cation, and the charge of Fe is 3. So, we will add this oxide in this analysis. Okay. And in garnet you basically have many different oxides are present. So, the number of oxide is automatically will increase compared to the last analysis. Okay. So, for example, if we have this is the analysis of your garnet. Okay. This is the analysis of the garnet, and it has a SiO2, titanium oxide, chromium, aluminum oxide, FeO, MnO, MgO, and calcium oxide. So, 1, 2, 3, 4. So, these 8 oxides are major oxides are present, major elements are present in this garnet analysis. And garnet is aluminum rich phase. So, it has a very high proportion of Al2O3. Okay. So, if you see this analysis, what we should do? We should try to see what would be the total of this analysis. So, we will write down the total, and we will use a equal sign and then sum in bracket, and we will see what would be the total of this analysis. So, if you see this total is very close to your 100%. So, as I said that in case of your anhydrous mineral, if the total is between 98.5 to 100.5. So, your analysis is good, and these in your garnet, this is anhydrous, this is nominally anhydrous mineral. There are some proportion of water could be present, but is in a ppm level. So, so your analysis is pretty good. So, we can use this analysis to calculate the mineral formula for this garnet and the end member for this garnet. Okay. So, we will follow the same procedure, and what we will do, we will basically take weight percent of SiO2 divided by the molecular weight of SiO2 multiply by the total number of cation present in SiO2. Okay. So, we have the B15 cell, that is your SiO2 weight percent, and these are from the electron probe. These weight percents are already from the electron probe. So, we can easily get we can just get this different oxide proportion from the electron probe. So, to calculate the atomic proportion of silicon, what we will do, we will take a SiO2 weight percent divided by the molecular weight of SiO2, that is a B4 cell, and multiply by the total number of silicon atom present in your SiO2. So, that is 1. So, C4 cell, and I use this dollar sign in front of the letter C and B. So, when you take a next proportion, so it will automatically give you the that cell. So, these are the your Si proportion, atomic proportion of silicon, and you can scroll this and you get a proportion of different cation present in this garnet analysis. Okay. So, if we see the total of the total number of cation present in this analysis. So, if we use a sum this option equal sign and sum, and we take all the cation present in this analysis. So, the total number of cation is now 1.859, and what we have to do, we have to calculate the proportion of your the mineral formula of garnet based on a 8 cation. So, we have to normalize the proportion of different these cations based on the 8 atom. Okay. So, what we will do, we will follow the same method, and we will take your to calculate the silica proportion normalized to 8 cation. We will take this silica proportion, that is a B25 cell, multiply by 8, because we are normalizing to the for 8 cation, divided by the total number of cation, that is a B34 cell, and we use a dollar sign in front of this B and this number 34. So, it will always fix to the B34, and we press enter, and it will give you the proportion of silicon. Similarly, we can get a proportion of the your these different cations, tetravalent, trivalent and divalent cations. Okay. And now this total is 8. So, this is the proportion of different cation based on your 8 this cation, and to calculate the Fe3 plus concentration, because in this particular in this calculation we only have Fe2 plus. So, to calculate the Fe3 plus concentration, we should calculate the net charge in this analysis. To calculate the net charge, what we will do, we will suppose we want to calculate the total charge of silicon atom. So, the atomic proportion of silicon atom, that is the 2.961 in this analysis, multiply, if we multiply by the charge of silicon, that is a 4, that will give you the net charge of the silicon in this garnet analysis. So, what we will do, we will take this to calculate the charge of silicon, we will take atomic proportion of silicon, that is based on a 8 cation. So, that is a B37 cell multiply by the net charge of the your silicon, that is a 4. So, if you multiply these two, you will be, your value will be close to 11.844. Similarly, we can calculate for titanium. So, if you scroll down, and so it will, program will automatically calculate the net charge of, so total charge for this garnet analysis. Okay. And if you sum all the total charge for this garnet analysis, so we already have calculated that the tetravalent cation and trivalent cation and your divalent cation, the total charge for the garnet will be 24, but here your net charge is less than 24. Okay. So, it means that the remaining charge will be your Fe3 plus proportion, okay, in this garnet analysis. So, if you see the charge difference for based on 24 net charge, so if you subtract 24 with the total charge from this analysis, that will give you the Fe3 plus proportion in this analysis. Okay. But there are certain conditions, and the condition is that this charge difference value, that is equivalent to your Fe3 plus proportion. Okay. That is equivalent to your so this is basically your Fe3 plus proportion. Okay. But sometime what happens, that this charge, because sometime the total charge in the analysis will be more than 24. So, in that case this charge difference will be negative. Okay. So, it means that we should use some function which can separate the charge difference of that is your Fe3 plus proportion in this analysis. Okay. So, basically what we are doing here, we are basically now, because we know the proportion of silicon to calcium in this analysis, only we have to separate the Fe present in this garnet analysis to the Fe2 plus and Fe3 plus, and we already know that this charge difference is in a positive term. Okay. And so, this is our Fe3 plus concentration. Okay. So, we will use another cell here, that is a Fe3 plus and Fe2 plus, and when we try to write down the silicon proportion, so it will be exactly equal to the your this B37 cell, that is your this cell, where we calculated the silicon proportion based on a 8 cation. Okay. Similarly, titanium we can put this B38 cell, chromium B39 cell, aluminum your B40 cell. Only when it comes to iron, okay, only when it comes to iron. Okay. So, iron, you see that iron is close to this equal to this charge difference. Okay. But here what we will do, we will use a IF function. Okay. So, this IF function is very useful. So, basically it will give you your calculation value is true or false. So, to know little bit more about this IF function, you should try to read a few books in which how to work in the Excel program, if you get in the internet. So, you can learn little bit about IF function. So, basically this function is very useful to tell you the true value of the analysis. Okay. So, what I am doing here, I am using a equal sign. Okay. And then I am writing in capital IF function, then I take a bracket, and in the bracket I am using a B58 cell. Okay. So, B58 cell is basically your basically this charge difference. So, 24 minus the whatever total charge we calculated from this analysis, that is the 23.89. Okay, 3. So, this number should be always a positive. So, in IF function we will use this less than 0, and it should not be equal. So, if in case of if this charge difference value is negative or 0, it will automatically Fe3 plus concentration in this calculation will be your 0. Okay. You can check this. So, we can basically, if we write down a 0 value, so you see that it automatically changes to Fe3 plus concentration is your 0. Okay. So, or if it will be a negative value, suppose if your total charge calculated total charge is more than 24. So, your charge difference will be negative. So, automatically it will give you a 0 value in Fe3. So, already we have this function if function. So, if function you use a equal sign if in bracket your this cell B 58 and you use a less than 0 or equal to 0, then you should use a bracket. We should also use another this condition, and again we will use a if function, and in a bracket this charge difference value should be always less than your total iron proportion. Okay. If it is more than your B 41 cell, that is your total iron proportion, so it means that it is a false value it will give. Okay. So, we should put this condition. Okay. And then we will use a B 58 is more than B 41 comma 41 and B 58. Okay. So, when we will use this if function, okay, so these two conditions, it will give you exact value of the Fe3 plus proportion. Okay. And here we have we subtract from this from the total iron proportion, that is your B 41 cell, and B 41 cell is your we already calculated the iron total iron proportion based on the 8 cation. So, if we subtract from the total iron from the Fe3 plus calculated value from the charge difference, so we can get Fe2 proportion. Okay. So, from this and all the Mn, magnesium and calcium is exactly the same from the calculated cation proportion based on 8 cation. So, so in this way we can calculate the proportion of your different cations present in this solid solution of garnet. And if you see here, what you will observe that in the silicon is less than 3. In the general formula of your garnet, you have a 3 this silicon is basically a 3. Okay. So, if you see the tetrahedral coordinated silicon is less than 3. Okay. So, it means that some of the aluminum will go to the tetrahedral side. So, you can easily calculate the aluminum which will go to the tetrahedral side, and that is you can calculate if you subtract the silicon proportion 3 minus silicon proportion, atomic proportion. So, it will give you a aluminum which will go to the tetrahedral side, and if you subtract this from the total aluminum, if you subtract the tetrahedrally coordinated silicon from this total aluminum, so that will give you the tetrahedral so octahedral coordinated aluminum proportion. Okay. So, basically you can calculate the tetrahedral coordinated aluminum proportion, and you can also calculate the your octahedral coordinated aluminum proportion. Okay. So, you basically get these kind of information from this analysis, and now your cation proportions are based on the ferrous and ferric iron proportion. Okay. And your total charge is 24 and total number of cation is 8. Okay. So, you can write down the general formula. So, first you will write down the divalent cation. Okay. So, Mg is 2.093 atomic proportion, iron is 2 plus is in 0.519 proportion, your calcium is in 0.338 proportion Mn. So, you can write down, and when you add this divalent cation, the total is 2.976. Okay. So, it is close to 3. In the general formula, the divalent cation total should be 3. Similarly, you can write down the trivalent cations, and trivalent cation you have a aluminum Fe3 plus. So, this is basically here you have a 2 plus iron and here you have a 3 plus iron. Okay. So, you can write down the aluminum 3 plus, Fe3 plus and chromium 3 plus, and from this calculation you can write down the proportion, and then if you add this, this will be close to your 2.009. So, you can add the divalent cation, okay. You can add the trivalent cation, okay. So, trivalent cation is basically you have this Fe3 plus chromium and an aluminum which will go to the your 6-fold coordinated side, not the 4-fold coordinated. If you take a total aluminum, so aluminum is going to the 4-fold side and 6-fold side also. So, you should only use your 6-fold coordinated aluminum, okay. And when you add this, it will be close to 2.009 and it is close to 2. So, it means that trivalent cation, the total number of cation is close to 2, and aluminum already we placed in the tetrahedral side. So, the total will be close to 3. Okay. So, this is the general formula for your garnet, and we know that in your garnet we have a 2 different group. One is your this pyrrole spite series, okay, and another one is your Jugendite series. So, pyrrole spite series is basically 3 minerals are present. So, you have a pyrope. So, PRY is used in this abbreviation. So, you have a pyrope, and pyrope is a Mg end member. Then you have a almandine, and this Al is used. So, PYRAL, and then spacetine. So, Sp is used. So, this pyrrole spite. So, this pyrope is a Mg end member, almandine is your Fe end member, and here you have a 2 plus Fe2 plus, and then Mn this spacetine is a Mn end member. Okay. And in Jugendite series we have uvarovite. So, uvarovite, that is a calcium chromium this garnet, rich garnet, this andradite, and then you have a grossular. So, in the pyrrole spite series, your Y side you always have a aluminum, okay, and in case of your Jugendite series you have in X side you have a calcium. Okay. So, so we have to calculate these 6 end members. To calculate this end member, if you see the pyrrole spite series in which your this X side you have a Mg, Fe and Mn in these 3 end members, okay, in pyrope, almandine and spacetine. So, if you see the Mg, okay, so Mg is only going to the pyrope end member. Okay. So, if you see here, okay, so your Mg is going to the pyrope in the pyrope garnet only. So, we already know the Mg proportion in this calculation, that is a 2.093. So, what we will do, we will if we take a proportion of Mg divided by the total divalent cation present in this X site, okay, multiply by 100, that will give you the pyrope, because the Mg will only go to the pyrope. Okay. So, from this calculation we can calculate the pyrope proportion. Okay. So, if you see here we have this is your Mg proportion, atomic proportion of Mg divided by the divalent cation. Okay. So, divalent cation total is your 2.976 multiply by 100. So, this will give you the your pyrope proportion in this particular garnet analysis. Similarly, your Fe2 plus will go to the only almandine. Similarly, we can do this for the for almandine proportion we can calculate, and we know that we have a Fe2 plus, that is a 0.519 atomic proportion is present in this analysis divided by the total of the divalent cation multiplied by 100. So, it will give you the Almondine proportion. Similarly, we have the Mn, and Mn is spacetine, Mn will go to the spacetine only. So, to calculate the Mn proportion, what we will do, the spacetine proportion, what we will do, we will know this Mn proportion, that is a B67 cell divided by the total this divalent cation multiplied by 100. So, that will give you the this 3 end member in the garnet. So, it is very easy to calculate the pyrope, almondine and spacetine proportion. Okay. To calculate the calcium rich end member, because calcium is going to the ivarovite, andradite and grossular garnet. Okay. And so, what we should do, first we should try to calculate the proportion of your uvarovite and andradite. Okay. In uvarovite formula, we have this chromium, and chromium will only go to the uvarovite. So, we can easily calculate the proportion of uvarovite. What we will do, we already have a proportion of chromium, that is a 0.098, and this cell is your basically this B63 cell, and if we divide this from the total trivalent cation present in the your Y side, okay, that is a 2.009 and multiply by 100. So, this will give you your uvarovite proportion. Okay. So, this will give you your uvarovite proportion. Okay. Similarly, your Fe3 plus will go to the andradite. Okay. And to calculate the proportion of andradite, what we should do, we should try to take a Fe3 plus proportion, which we calculated from the charge difference or from the charge balance. And so, if we know the Fe3, we already know the Fe3 proportion, okay, divided by the total trivalent cation in the Y side multiplied by 100 will give you this andradite proportion. Okay. So, andradite and uvarovite is very easy to calculate, okay, but in case of grossular, the formula is Ca3Al2Si3O12. So, basically calcium is present in the X side and aluminum is present in the Y side. Okay. So, basically if we add these three, the total calcium is going to this uvarovite, andradite and grossular garnet. It means that if we try to add the proportion of grossular plus andradite plus uvarovite, that should come from the calcium, because calcium will go to only in this 3 mineral. So, if we try to calculate the total of these 3 end members, that is your calcium proportion B69. Okay. So, B69 divided by the divalent cations, okay, that is magnesium, iron, manganese and calcium. So, that will give you the proportion of your grossular, andradite and uvarovite. Okay. So, from this we can calculate the total proportion of these 3 end members, and if we subtract from this grossular plus andradite plus uvarovite minus uvarovite plus andradite, that will give you the grossular garnet proportion. So, I just subtract this grossular plus andradite plus uvarovite minus in bracket sum of the uvarovite and andradite. So, that gives us the proportion of your grossular garnet, and if we add these 6 end members, the end member total should come to the 100%. So, if our calculation is correct, this calculation is close to 100%. So, this is the way we can calculate the end member for garnet, and we can calculate from the charge balance or from the charge difference, we can calculate the Fe3 plus proportion. So, these 2 examples I gave you for olivine and for the garnet. For other minerals, if you are interested, for example, if you are interested for calculating the end member for pyroxene and for plagioclase and some other mineral. So, I will suggest you to use this book, and this book is basically an introduction to the rock forming mineral by D. Harvey Jusman. And if you go to the appendix, and this at the end of the book there is the appendix 2, and in this appendix 2 you can 3 your end member calculation methodology is given. So you can learn about the end member calculation from this book, and also you can take few other example to calculate the mineral formula for some hydrous mineral, and you can learn about this. Okay. So, I will stop my lecture here, and we will meet sometime in next week. Thank you.